All right, let's start out with our first introduction to nomenclature. Nomenclature is just a specific set of naming rules. So nomenclature, the word, isn't specific to chemistry. A lot of you in class are doing some medical terminology stuff, and you could call that medical nomenclature. If you are a baseball fan, you know the lingo of baseball, like on-base percentage and slugging percentage and ERA and WHIP. That's baseball nomenclature. If you're a dance major and you know a lot about dance, you would know a lot of the nomenclature of dance. So nomenclature just means kind of like a naming or a vocabulary for a specific like or interest or subject. There you go. So we're going to focus on the nomenclature for ionic compounds today. And we really have two different types of compounds that we're going to investigate. The first we'll call type 1 compounds. Remember, ionic compounds contain both a metal and a nonmetal. They're very strongly held together. They have high melting points traditionally. So we're going to focus on these ionic compounds that are called type 1 compounds. Here's an example of a type 1 compound, something that's formed between sodium and between chlorine. And let's kind of rehash the reason as to why these two things come together. Again, Na has that extra valence electron in its outer shell. It's got that one extra electron. On the other hand, Cl has an outer shell that's got 7 valence electrons. So Na wants to get rid of that one electron so that it has a full outer shell, and Cl does not mind accepting it. And so we have that transfer of electrons. When that transfer occurs, we no longer have this outer shell 1 electron, and chlorine now can be said that it has a total of 8 electrons. There we go, 8 electrons. That has the effect of making chlorine negatively charged, and also has the effect of making sodium positively charged, 1 plus 1 minus, because there was 1 electron transitioned. We know that there's an attraction between oppositely charged particles, so these things come together to form NaCl, sodium chloride, NaCl. Okay. Type 1 compounds are the compounds that are made with metals that reside in group 1, 2, or 3 on the periodic table. And I got to go ahead and define what those groups are. So this is kind of like a rudimentary periodic table. Okay, there we go. So these are group 1 metals. Hydrogen would be on the top of those. We know hydrogen's not a metal again, but it does fit over there because of the valence electrons that it has. These are group 2 metals. Okay, that's like the calcium-magnesium row. And then these are the group 3 metals. So you got to make sure that you skip the great divide right here. So you've got 1 here, 2 here, and 3 here. So those columns are headed up by hydrogen. It would be right there, and then beryllium would be right here, and I think boron would be right here. So that's group 1, 2, and 3. So here's how we name these things. First of all, we name the metal per usual. So whatever it is, if it's Al, we call it aluminum, or if it's Na, we call it sodium. So there's nothing different there. So in the example of NaCl, we say sodium. And then the second part of that is we change the ending of the nonmetal to IDE. So when sodium and chlorine come together, it's not sodium chlorine, it's sodium chloride. Okay, pretty simple. What about subscripts? We don't really mention them at all. And the reason is because they're implied by the known charge of the elements. All right, so let me give a couple examples of these. I'm going to go with something besides sodium chloride. Let's try Na2S. All right, so the rule is we name the metal, and then we name the nonmetal, but we add IDE to the ending. A lot of people say sulfuride at first, but no, it's actually sulfide. So this is sodium sulfide. We don't have to worry about this subscript. Again, let's figure out why that is. Well, sulfur is always 2 negative, and so it always gives the charge to 2 negative. It always wants to accept 2 electrons. So that means there always has to be 2 sodiums that pair up with the sulfur atom. So we know that that subscript 2 is going to be there. We don't have to say like disodium sulfide, or sodium 2 sulfide. No, we don't have to say that. Sodium sulfide will suffice. Sodium sulfide. So these are kind of like the easiest types of compounds to make, or to name. Let's look at another one. CaO. Okay, that's calcium oxide. All right, let's look at something that looks a little bit more complicated, but it really isn't. Let's look at this guy, Al2S3, okay? This is the same idea. We don't really care about the subscripts. This is just aluminum sulfide, okay? Now, we're also going to have to go the other direction, so I may give you something like this, magnesium fluoride, okay? So we know that magnesium is Mg, and it is a group 2 element, so it's got a charge of 2 plus, and fluorine is a 1 minus. So the fluoride, the IDE ending, doesn't really bother us right now. We treat this the same as we have been in the past. We crisscross those numbers, and we come up with MgF2. That's magnesium fluoride, okay? Now, the one goofy thing with this is the reducing principle, or the reducing property. Let's say I've got something like calcium sulfide, and I want to see what that forms. So calcium is Ca, it's a group 2, so it gets a 2 plus, and sulfur is a 2 negative. And let's see, a crisscross, so I get Ca2S2. That would actually be incorrect, because with these types of compounds, we are writing their empirical formulas, so we need to reduce the subscripts. So CAS is the correct answer. All right, so those are type 1 compounds. Let's go on to type 2 compounds now. These are ionic compounds where the metal is actually a transition metal. We haven't been talking about these a lot over the past couple of days. Well, now we finally start talking about them. Again, we got to figure out what a transition metal is. Transition metals, if we take a look at a periodic table, again, I'm going to try to draw one here. Okay, transition metals are all the metals right here. These are the TMs, the transition metals. So gold is in there, and silver is in there, and copper, and cobalt, and tungsten, and osmium, and all of those things. Those are all transition metals right there. Now, actually, there are a couple right here, too, that you actually have to be concerned with that we call transition metals. So, normally what we would do is we would kind of like create a division line right here, and we'd say, okay, everything that's in this orange box is a transition metal. Well, I have to alert you that lead, and tin act as transition metals, as well as some other things down in that area, like bismuth and indium and thallium, but we don't use those a whole heck of a lot. So these are the two, lead and tin, that are also transition metals. They fit the mold of these guys in the orange box. Okay, how do we handle these? Well, transition metals are goofy because unlike group 1 or group 2 or group 3 metals, transition metals do not all have a set number of valence electrons. Like, you can look at all group 1 metals and say, oh, they all have 1 valence electron. Group 2, they all have 2 valence electrons. If you go into the group where chromium and molybdenum and tungsten are, you don't know exactly how many valence electrons there are. The reason why is beyond the scope of this class, but it's just the way it is right now. So we don't always know what their charges are. So charges need to be defined in the compound's name in order for us to know how these transition metals are going to bind with other anions. So here's the process. We name the cation and the anion just like type 1 compounds. There's no difference. But like I said it before, we have to be able to define the compound's charge. So we are going to place a Roman numeral between the ion names. So you've got the cation, which might be iron, and the anion, which might be chloride. And we leave a little space in there, and we're going to place a Roman numeral in there. And that Roman numeral is going to actually designate the charge of the transition metal. So let me show you how that's going to work. I'll give you an example here. Okay, let's just, the one I just said. All right, FeCl3. Okay, good. So FeCl3. We know Fe is iron, so we just write iron. And we know Cl is chloride. And then we find iron on the periodic table, and we see, oh, it's a transition metal. That should tell us right away that we have to leave a little space right in there. We need a Roman numeral to tell what the charge on the iron atom is. How do we do that? We do the re-crisscross process. Remember how we crisscross charges in order to get subscripts? Well, we now have to undo that. We bring the 3 here, and we bring the 1 there. So we have Fe3 plus and Cl1 minus. Now we have to do a check. Is chlorine really 1 minus? Yeah, it is. It's always 1 minus. it is in that column that always is 1 minus, 1 negative. If it's 1 negative, well, then that 3 means that that is the charge of the iron. So we got iron 3 chloride. I'll tell you what, here's what a lot of people will make a mistake doing. Okay, they'll say this FeCl3, and they'll say, oh, right here, there's only one Fe atom. So instead of saying iron 3 chloride, they will say iron 1 chloride. That is not correct. The Roman numeral does not talk about the subscripts. Instead, it talks about the charge or the superscript on the cation. So iron 3 chloride is indeed the correct answer. Let's go the opposite way now. Let me give you a compound. Let's go magnesium. That's not transition metal. How about manganese? There we go. Something that sounds like magnesium. So manganese, let's see, manganese oxide. Now it's a transition metal, so you need to know what the Roman numerals are in between the manganese and the oxide. So manganese is Mn. You don't know what the charge is because it's a transition metal. So you have to refer to the Roman numerals. Mn is 2 plus. Oxygen is 2 minus. We crisscross them. What do you notice? The subscripts will be the same, right? Mn2, O2. So what do you have to do? Reduce, reduce, reduce. So this is the formula for that stuff. All right. Let me show you one really tricky one, right? Chromium. Actually, I want to go the other way. Let's say Cr. Let's call this one CrO. Okay. All right. So let's name this first. All right. Cr. Okay. Well, that's chromium. Let's see. Chromium. Good. And O, that's oxygen. So oxide. And I know that chromium is a transition metal, so I've got to have Roman numerals. All right. Now, let's see. Cornick said I got to re-crisscross my charges. Okay. So one up there. This one up there. There are no subscripts. Well, that must mean that I have Cr 1 plus and O 1 minus. So that must mean my Roman numeral is 1. No, you are wrong. You are incorrect, incorrect, incorrect. Why is that? Because what did I say you had to do? You had to check that the charge on the anion is correct. And oxygen is not 1 negative. Oxygen is in that column that is traditionally almost always 2 negative. So you have to make that thing 2 negative. Well, how would you do that? Well, you got to multiply it by 2. 1 negative times 2 is 2 negative. But if you do it to the oxygen, well, you got to do it to the chromium as well. 1 plus times 2 is 2. So the actual charges on this compound are right here. And when I crisscross them, they actually reduced. That's why I had this guy. So chromium is actually chromium 2 oxide. All right, there you go. That's ionic nomenclature of type 1 and type 2 compounds.